Welcome back. In the last episode, we built a unique pointer. It was fast, efficient, and leak free. But it had one strict rule: only one person can hold the list at a time. And that has created a problem at North Pole. Imagine Santa needs to check the names on the list, but at the exact same time, the head elf also wants to access the list. If Santa moves the list to the elf, poof, Santa loses access. If he makes a photocopy, we waste memory. And worse, if the elf makes a change, Santa's copy is instantly out of date. We don't need to move and we don't need to copy. We need to share. We need a way for multiple people to hold the same list. Keeping with the Christmas spirit, today we will learn to share. Welcome to episode 5 or Learn C++ with me. Today we're building shared pointers and reference counting from scratch. So let's jump in. So, how do we do it? The logic behind what is STD shared pointers is a technique called reference counting. Imagine that we attach a small tally counter to our list on the heap over here. So what are the properties of this counter? When Santa creates the list, the counter is at 1. There is one reference or one person holding the list. When an elf copies the list, we don't make a copy in the memory of the list array. We just copy the pointer and we increment the reference counter to 2. When Santa leaves the room or the list object goes out of scope, the destructor is called. On each invocation of the destructor, we decrement the tally counter. The list stays alive because another elf might be holding it. When all the objects goes out of scope, when all the elves leave, the the tally counter goes to 0. Since the count is 0, we can finally hit the delete button and deallocate the memory for the list. So let's modify our code. We need a place to store this count. It can't live in the object itself, like so, because all the copies need to see the same count. So we need to allocate the reference count on the heap. For now, we're commenting out the size member because it adds some complexity, but don't worry, we will add it back later. In our constructor, we now need to make changes to add the reference count. When the object is created initially, we allocate some space for it and set it to 1. Now we modify the copy constructor, but with a twist. Instead of a deep copy, which is copying all the data, we do a shallow copy, much like the move operator, of only the pointer. We point to the same list and to the same reference counter, and critically, we increment the count. So let me modify the code for that. So when we're copying an object, it'll have the same list and the same reference counter. We will not allocate a new list because we're doing a shallow copy. Critically, we will increment the ref count. the value at ref count. We're not doing new allocations. Yes. What about the move constructor? Well, what we're doing is that we're just moving the shared list from one elf to the other. So we don't need to increment the reference count. Also, when an object is moved, we say we make the right hand side null because it's understood that it will not be used. It becomes a temporary value. That does it. Before coming to the copy assignment and the move assignment, let's first talk about the destructor. The destructor now has a condition. We don't blindly delete the list when the object goes out of the scope. We first check if there are any references left. So first we will decrement the reference count and then check if the reference count is 0. Only then do we delete the list and the reference count because we are allocating two things on the heap. Now we come to the assignment operators, the copy and the move assignment operators. They follow a similar logic. First, we clean up the old reference, but cleaning up the old reference is not simply delete now. It's this whole process of cleanup. So let's make this into a function so that we're not repeating ourselves. And instead of delete, called cleanup. Then we copy the reference count and the size. We're not allocating any new list. We're just doing a shallow copy. The only thing we're doing is we are incrementing the reference count. When it's a copy assignment, that is when two elves are now sharing the list. And when it's a move assignment, that is where giving a handle to the shared list to a new elf, we're not even incrementing the reference counter. We're just nullifying the RHS. There's one more thing. For now, we will comment out pushback for the specific example because resizing a raw array is a little complex because if one person reallocates, then the other are left holding a dangling pointer. We will add it back later. With this, we have covered our rule of 5 operations. In the destructor, we added the ref count check. In the copy constructor, we added the increment of ref count and we only created a shallow copy. We did the same thing in copy assignment, and the move assignment and the move constructor remain almost the same. Let's add some printout statements to our code and visualize the shared pointer. Here, I have added the printout statements. These printout statements display the reference count after each operation, covering construction, the plain variety, copy and move, the assignment operators, copy assignment and move assignment, and the destructor with one where the ref count is decremented and another when the destruction is complete. Now let's examine the driver code sequence. A list V is created by Santa, W copies V, U copy assigns W, corresponding move operations create A and B, W and B go out of scope, die, and finally V goes out of scope. Take a moment to consider what the outcome will be. Let's compile and run the code. So we compile the code, we run it, and we get a segmentation fault. So what's happening? First, list V is created and the reference count becomes 1. Then W copies V. So the reference count is incremented to 2. No new list is allocated. Then when U is created, this is a new list. This is like an elf starting on its own with a new list which has a reference count of 1. And then when U is copy assigned from W, the list that U was holding is decremented to 0, is deallocated, and another pointer or another handle to the shared list is assigned to U from W. Now when we move the list from U to A, the list with U is just nullified and the reference count does not change. Same when list is moved from B to A, the list that B was holding is decremented to 0, is deleted, and the handle is moved without incrementing the reference count. Now what happens when W and B go out of scope? Their destructor is called and we decrement the values. But these are not the only objects which are going out of scope. A is going out of scope as well. U is going out of scope as well. Well, these objects have moved. So let's see what happens when their destructor is called. The destructor tries to dereference the reference count. But when the objects were moved, we've already nullified them. Ideally, a nullified object should not be used, but its destructor is called automatically. Therefore, we will add a guard onto our cleanup statement for this condition, that if reference count exists, only then clean it up. Otherwise, we know the object has already moved. So there are other places where this reference count is dereferenced as well. So for example, in a copy constructor. But the thing is that if we are trying to copy from a object which has already been moved, we should expect an error or the program to give a seg fault. Now, how you handle this is a design decision. And currently, in my simple example, I'm not handling that. I'm very happy for my program to give a seg fault if someone is trying to copy from a moved object. Now let's compile and run it again. Did we save the code? Yes. After W and B die, we see two decrements of the reference count. Then we have the printout statement. We print ref count where the reference count 1 is printed. When V goes out of scope, the reference count for the main list goes to 0 and the reference count, and finally the list is deleted. So here we have it. Here we have it, my friends. Take a moment to let it all sink in. By simply tracking how many people are holding a list, we have recreated the logic of shared pointer as it is in the standard library. We now have a memory safe shareable pointer that cleans itself up automatically. Next, we will add the pushback again. We had removed the pushback function. We did that to wrap our head around the life cycle of the code. But now it's time to put it back. So, what do we have? We have the life cycle working. We can share the list, count the owners, and destroy it when the last person leaves. But now we need to add more things to the list. And this brings up a tricky problem. If the Santa calls pushback as it is now, a new list is allocated, and in effect, what we see is that the list has moved to a new address. But if Santa just moves the list to a new address and forget to tell the else will be left staring at the old deleted memory. So in this pushback function, the new list that is allocated updates only the list variable of the object calling it, and that leaves the other objects with a pointer pointing to the old deleted memory. That's a crash waiting to happen. To solve this, we use a technique called indirection. Instead of pointing directly to the data array, our nice list points to a shared manager or a control block. It's just a variable on a heap. And that's our new variable, reference to list, a pointer to pointer. Think of ref list as a shared whiteboard on the wall. Both Santa and elves look at this whiteboard to find the current address of the list. And we're calling these three variables taken together as the control block. When Santa pushes back a value, he allocates new memory and then simply erases the old address at ref list and writes to it the new allocated address. Since now Els and Santa are looking at the same whiteboard, they automatically get redirected to the new list. And we've done the same with size as well. We are, instead of having a local copy of size, all the objects will read the size from the address referred to by the ref size variable. Ref list, ref size, ref count. So what's happening here? Ref list itself is now a valid pointer to some chunk of memory. Maybe say the address 40. But the content of that memory is a null pointer. So we have ref list, the value at ref list is ox40, and this is the place where our list will be, but initially then there's no list, so it points to null pointer. So that is what this all crucial, all important line means. Ref size, this is a simple one. It just tracks how many slots we currently have in our ref list. Because the list doesn't exist, it is 0, and ref count remains the same. First, to get the list, we will need to dereference the list at this address. And to get the size, we dereference the address of size. We allocate new memory. We copy the data into the bigger array. We delete the old array. And then these steps are a little redundant. We point the list to the new list and add the increased size to write the value. Next, we will update the address at which this list is present and will update the size. By doing this, we have established a solid internal state. Our smart pointer is now ready to safely manage memory and start tracking references. Next, we update the destructor to delete both the array ref list and the data pointed to by it. We delete the actual array we delete the list, the address at which this was stored, and we delete the place where we wrote the size. So basically we delete everything that we ever allocated. We now update other member functions. Let's start with the copy constructor. As before, we just create a shallow copy of the RHS into the newly constructed nice list. Let's update the move constructor. Again, we create a shallow copy. We just change the handle from the right hand side to the newly created variable and nullify the variable at the right hand side. Notice that this ref list equals null pointer is different from the one in the vanilla constructor, because this literally puts it in an invalid state, that there is no place where we're tracking the list, and which is different from that there is a place we're tracking the list but the list is 0. So be careful about this one. Next comes the copy assignment operator. Again, we do a shallow copy. We're not allocating anything new. We increment the ref count and we return this pointer for chained assignments. Simple enough. Next, we update the move assignment operator. Again, we create a shallow copy, or rather we steal the guts of the right hand side. Wouldn't it be so much easier if we had the whole control block in one struct? Something to think about. We'll see it later. We nullify the right hand side. Again, simple enough. We've already updated the pushback and we've already updated the destructor. So we're good to go. Let's compile and run the code. So let's look at the driver. So let's look at the driver function. It's the same one we used to illustrate the life cycle. I have just added pushback after every copy and move operation and a print list at the very end. So Santa creates a list adds 5, passes it around to elves who add 6 to it. Then, after copying, elf adds 7. After moving, another adds 8. New list is created. After that list is moved, an elf adds 9. So we should expect 5, 6, 7, 8, 9 to be printed when the Santa tallies the list at the end. Let's see what it does. Yeah, and that does it. That does it. This is like a list being passed around, added to by different elves, and Santa reading out the final results at the end. Some of these elves continue to look at the list, some of them move the ownership around, but we are able to maintain the list, work on it together without leaking any memory. Due to limitations on Python tutor, I cannot illustrate all operations, but here is a good example. Santa has added one item to the list. Two elves come and share in making of the list and add their own items. Let's go. So we set up in the constructor, we have these three member variables, ref count, ref list, and ref size. And ref list points to a location which is null at the moment, and ref size says the size is 0. When we push back, we allocate new memory, copy the value into it, and then write the address to the address pointed to by ref list. When we copy, we increment the reference count and just create a shallow copy to all the pointers. Again, in pushback, we allocate new memory, copy the existing data into it, delete the previous list, write the new data into it and update the size, and then copy this address into the location pointed to by ref list. This operation, and copy the new size into the location pointed to by ref size. So this essentially, these three variables on the heap are our control block. Same with U, reference count increases on its creation and it does a shallow copy. New memory is allocated, list is copied, new data gets written, and the address on the shared whiteboard is updated for all the else. Great. Now let's look at cleanup. When U goes out of scope, it only decrements the reference count. So the reference count goes to 2. Then W goes out of scope. The reference count decreases again to 1. But crucially, nothing happens to the whole array. The Santa can still see the entire list. Now, U and W have gone out of memory and the Santa is left holding the whole list, and we have noted that the reference count is 1. Again, we call the destructor, We decrement the reference count. It is 0. We delete the list. We delete the address at which we were tracking the list. We delete the address at which we were tracking the size. We delete the address at which we were counting the references. And bravo. We're done with our program without any memory leaks. By the way, what we have just built, where we resize the list and update it for everyone, is exactly how std shared pointer brackets vector work in the standard library, because a vector resizes the data as well. The shared pointer manages the whiteboard, the address at the three addresses in which we were storing the count, the list, and the size. And vector manages moving the data array. That was the pushback function. And there we have it. And there we have it. A fully functioning shared pointer. Santa and elves are happily sharing the list. The memory cleans up after itself. Everything is perfect. Since I'm releasing this on Christmas Day, it feels appropriate. It is the season of sharing, after all. Right now, our reference count dies when the object goes out of scope. But what if we need the count to survive longer than the object? Imagine an intern elf, perhaps not actively working on the list but maintaining an observation post. To address this case, next week we will do a bit of architectural housekeeping, building a proper control block and implementing that final pointer to complete the set. This simple change is key to unlocking weak pointers. By the end of the next video, you would have built all the three pillars of C++ memory management: unique pointers, shared pointers, and weak pointers completely from scratch. So, subscribe so you do not miss the finale. Happy coding, Merry Christmas, and a happy New Year. See you in the next one. Cheers.